Welcome to the lecture. Today our topic is FIR filters. So FIR filters are finite impulse response filters and they depend only on the inputs and they don't depend on outputs, previous outputs. An FIR filter is completely specified by the following input output relationship. Y1 is equal to summation I 0 to k bi x n minus I. So what bi here is? Bi is basically the filter coefficient and the length of filter will be k plus 1. If we take the z transform of the previous equation, that is this one, it will be like this one. Just change the time domain variables in z domain and delay as a multiple of z power. So if we factorize and solve and form rearrange this in the form that y over x, it will give us the transfer function of the filter and it will be like b naught plus b1 x z of minus 1 plus up to z bk z of minus k. Let us discuss an example. We have y of n filter FIR filter y of n is equal to 0.1 x of 1 plus 0.25 x of n minus 1 plus 0.2 x of n minus 2. What we will have to determine is we will have to find transfer function, filter length, non-zero coefficients and impulse response. So first of all we should take z transform of the given filter. After taking z transform, just what we will have to do is just y over x is output over input. Output over input is basically the transfer function of the filter. So transfer function, our first objective, the transfer function is this one, and if we want to find the filter length, the highest power is 2. So k plus 1 is 2 plus 1 is equal to 3. The length of filter will be 3 and the constants are the filter coefficients. So b naught is 0.1, b1 0.25, b2 0.2. So if we again take inverse z transform of the transfer function, we will get impulse response of the filter. What this example tells us? This example tells us that the transfer function equation has constant terms. All the other terms are the negative powers of z, which means that all the poles are at origin on the z plane and the filter is stable, has only finite number of terms. The second thing that this equation tells us is FIR filter operation involve only multiplication, so its implementation is simply easy. If we want to design a filter, Fourier transform design method is used. Let us consider a simple low pass filter with normalized cutoff frequency omega c, whose magnitude in terms of normalized digital frequency is omega and is plotted in 7.1, this one. So the transfer function and is characterized by this one, 0 to pi, because maximum frequency in digital the maximum digital frequency is pi. Since the frequency response is periodic with the period of omega is equal to 2 pi radians, and if we apply the Fourier series, it will be like this one, the 7.5 equation, and the quotients of Fourier series will be like the following formula. We know that the Fourier series coefficients C of n is equal to 1 by 2 pi minus pi to pi integration h transfer function multiplied by the e of j omega naught n omega d omega for n minus infinity to infinity. This is the periodicity of the ideal low pass filter response. So in 7.5 and 7.6, if we again represent it in time domain, we will see that the omega n and omega naught will be 1. So substituting 1 in equation 7.6, which is this one, omega naught is equal to 1, it will come out to be like this, simple. Omega naught will disappear. So if we again if we take the z transform of the equation 7.5 and substitute back z is equal to omega naught is equal to 1, we will get the following formula. Just as we will take the z transform of this and substitute only omega naught is equal to 1, it will be like the previous one, this one. In this you can see that there are positive parts of z, which means that the filter is non-causal. It depends upon the advanced and past values of the input. So for n is equal to 0, the h of n will be like omega c over pi, and for n not equal to 0, it will be sine omega c n over n pi. So this is the z transform, and again symmetry. This is the graphical representation of digital low pass filter, impulse response of the digital low pass filter. And if we have, last time we said that if we have a simple low pass filter, we can design any filter, high pass, band stop. So all the other filters are derivatives of low pass filter. So if we have low pass filter, response of the low pass filter, we can find the responses of the high other filters by using this low pass filter. So this table clearly explains that the responses, impulse responses of all the filters. We have seen that h of when n is equal to 0, h of 0 will be omega c over pi in case of low pass, and in case of high pass it will be pi minus omega c over pi, because last time we've seen that low pass filter is high pass filter is all pass minus low pass, means 1 minus the response of low pass. So it will be like this one. Similarly, others. So that's it for today's lecture. In the next video we will see Gibbs effect, what is Gibbs effect, and how we can solve the Gibbs effect using Windows method. Thanks very much for watching.